Okay, let's get started, please. So, so the last couple of sections in this chapter. So this chapter, like I said earlier, is about these things called algebraic functions. Okay, so these are kind of like the simpler functions. And then this course is really, it's called transcendental functions. So, what we're really aiming for is to talk about these other functions, the logarithmic functions, the exponential functions, which are sort of like beyond the algebraic functions. Okay, so so 4.6 is about developing an intuition for polynomials. And we said last time that there's these facts about polynomials. There's like how polynomials behave. So polynomial behavior. There's certain things that they do and that they don't do. One is that they don't jump or skip. I guess jumping and skipping is kind of the same thing. I don't know why it's called, they separate these, but anyway, they don't jump or skip. Right, so you can't, if you see something like, well, hold on, I'll hold off on that for a second. They don't have corners. Right? If they're if of degree n, then they have at most n minus 1 turning points. And the last one was if we're looking at them when x is large, right? If x is a very big number, positive or negative, then the polynomial is basically like, it looks basically like its first term. Okay, so remember, polynomial is something that looks like this. Some constant times x to the n plus some other constant times x to the n minus 1 plus all the way down to the constant term. Right, so this is what we call a degree. This was a degree n polynomial, right? Okay, and so there are these. If we're talking about this degree n polynomial, then it kind of makes sense, right? When we're looking at x really large, then this turns out to be the dominant term, right? This term turns out to be the one that sort of dictates its behavior. These other guys are going to be much smaller, right? So because suppose n is suppose x is a billion, right? Or suppose suppose you have something like n is 3. Suppose you have something like this, and you have like 3x cubed plus plus 10x squared plus 1, or something like that. And you look at x when x is like 10 to the 6. Okay, right? So this term is going to be 10 to the 18, right? 10 to the 18, and you've got this 10 times 10 to the 12, and you've got a plus 1, right? But you see that when you get up to really large terms, then these terms this term isn't really going to matter with respect to, in comparison with this term, right? So the behavior of the polynomial is going to be dominated by its top term, right? This top term is going to dominate the behavior. Okay. Right. That's what this last one is saying. That if you're looking at it way out, away from the origin, then the top term dominates the behavior. Okay. So does that make sense? Yeah. Okay, so there are certain implications of these facts. What do these facts tell you? Like, what can they tell you about polynomials? Well, they don't jump or skip. So this basically tells you how to recognize when it's not a polynomial, right? If you see jumping or skipping, then you know it's not, right? So you can use this to tell if the function is not a polynomial, right? If somebody shows you something that has some sort of jump in it, or it has some sort of break in it, right? It's going like this, and then has a hole in it, and then goes onwards. You know it's not a polynomial, right? So I think this is probably what they mean by jumping, and this is what they mean by skipping. So you can use this fact to tell if it's not a polynomial. The same sort of, the second fact, same sort of thing, right? You can use it to tell if something's not a polynomial, right? If it's got a corner, you know it's not a polynomial, right? So similar purpose or similar use, right? The third one is kind of cool because it tells you, it tells you about how many turns you can have, right? So if you see something like this, I have corners. Okay, if you see something like this, right? And you say, okay, it's turned how many times? Well, 1, 2, 3, 4, 5 times. It's turned 5 times, right? Well, that tells you that it can't be of degree 5 or lower, right? Because if it's of degree 5, it can have at most 4 turns. This one has 5 turns, right? So this basically tells you, right? So right, if it were degree, so this thing has this one has 5 turns, right? And so you know that it can't be degree 5, and it can't be degree 4, 3, or 2, right? Make sense? Right? Because if it's of degree 5, it has at most 4 turns, but it has 5 turns, right? If it's degree 4, it has at most 3 turns, but it has 5 turns, right? So yeah, precise. Could be 6, yeah. So this has 5 turns, so must be degree 6 or over. Degree 6 or above. And it's not clear. You don't know what degree it is. Okay. Right. And number 4, if x is large, then the polynomial looks like this. So this one you can use. So if you see something like, okay, so this one basically tells you you can use to determine the sign of an. You can use to determine the sign of an. So, for example, this one here, right? So you've got this polynomial. And you see that, away from the origin, it looks like this, right? Far away from the origin, it looks like this, right? And so that first off, you know that this is going to be. Do you know if this is odd or even? This is something we mentioned last time. So, is this going to be an odd polynomial or an even polynomial? It's going to be an even polynomial, right? The top term is even because you see that the top term looks, it looks like, right? It looks like the x squared, like an x squared function, right? What we said last time is that if it's even, roughly it looks like a squared function, and if it's odd, roughly it will look like the cube function. Okay. So here you can see that the top term has to be positive, right? Because if the top term were negative, it would be going down like that, right? So, right. So you can, you look at this number 4 sort of says, look at the rough behavior, and then you can tell what the sign is, right? That the sign is going to be positive, okay. Right? If we saw something like this, right? Well, what kind of sign would you say was the top term? First off, is the top term positive? Is the top term odd or even? It's odd, right? Because it looks kind of like a Q function, right? And does it have a positive sign on it or a negative sign? Negative, right? Because it looks like that flipped over. Okay. Okay. So so let me put up a couple of examples, and you tell me what you can tell about them. What can you say about these polynomials? So, so here's the first one. What can you tell me about it? Here's the second one. Say, make it a little more complicated. And here's the third one. Okay, talk to somebody nearby. Okay, what can you tell me about, who would like to say anything about this first one? What can you tell me about it? Yes, Amy. It's even? Yep, so the top degree is even. even, right? Because in the when it's far away from the origin, it looks something like that, right? Okay. And anything else? It's got a positive, so the top coefficient is positive, right? It's positive, and what else? The degree has to be 4 or greater, right? The degree has to be greater than 4. Okay. What about this one? Anybody? It's too easy. Let's do this one. It's kind of the same thing. Yeah, still.
So it's a negative coefficient,
Right.
and the high score is going to be odd, and then it has 4 terms, so it would be a 5th degree.
Yes. So degree has to be 5 or over, and you know that it's an odd. So the degree is odd. Is everybody all right with that? Everybody all right? Any questions? Any questions? Okay. Let me write this thing out a little bit more clearly, right? So if it's degree n, it must have at most n-1 turning points, right? So if it's degree n, then the number of turns must be less than n, right? And if we, what does that tell you? It tells that if the number of degrees, if the number of turns is greater than or equal to n, then it's not of degree. It's not of degree n. So the degree actually has to be greater than n. Okay. So unfortunately, we can't really explain any of these things properly. Not until later. So this one would come in calculus 1, and then these two facts actually would come much later than that. To understand them really, you actually need to go pretty deep into mathematics. It's kind of interesting. But the one that we can explain is this last one. It can give you some sense of why this last one is true. Right? If x is large, then the polynomial looks like the top term. And so I kind of roughly gave you some sense of it over here, right? But there's a formal way to explain this. So let me show you that. Y is a polynomial basically like its top term if the absolute value of x is large. So I'm just going to give you some sense of how people make arguments in mathematics. So one way you can think about this is you can say, well, look, if we take this thing, an xn plus an minus 1, x to the n plus a1, x to the 1 plus ax plus a naught, we can rewrite it. And we're going to rewrite it as by factoring out an x to the n. Okay, so we're going to distribute out an x to the n out of everything. Okay, so we're going to get this 1 here. The second thing we're going to get is an minus 1 over a sub n and then we would have x to the negative 1. That will give us the second term. You guys see that? Right. Right, so this an x to the n times 1 gives us the first term. Right. An x to the n times this thing, well, that's going to give us the second term, right? Because we're going to, the a sub n's would cancel, we would get a sub n minus 1, and then we get these guys together, which is x to the n minus 1. Right, so multiply those guys together, that gives us the second term, plus, just for practice, let me ask you guys to write down the last two terms, just for, basic multiplication practice. Okay, let's think about it. What would we need to multiply this by to get a sub 1 x to the 1? Well, we want an a sub 1 divided by a sub n, right? Because when you multiply those guys together, that would give you the a sub 1, right? And then we also need x to some power, right? X times this thing should be x to the 1. So we need 1 minus n, right? Because x to the 1 minus n times x to the n would give us x to the 1, right? When we multiply this guy by a sub n x to the n, what's going to happen, right? We get this thing would cancel with that, and then the n would cancel with this n here. We'd be left with a1 x1. Okay. And then for the last guy, we do something similar. We're going to need a naught over x to the n, and then we need just x to the negative n, which would give us x to the 0, which is 1. Okay, so all we've done is factor out, we just factored out this a sub n x to the n. Prisa, yes.
Sorry to go
Yeah.
back, but for the a n to the x of it and then a n minus 1 to the x of it, why would it not be, sorry, on the left side?
This one.
Sorry, all the way up, yeah. To the n one?
Oh, I'm sorry, this should be n minus 1.
Okay, yeah.
Sorry, thank you, that's my mistake. Maybe that's why you all looked a little confused. Yeah, sorry about that.
Sorry, if you can review what the difference is, like, can you use like numbers to give an example of what the difference between the powers?
Sure. So yeah, that's a good idea. Make this concrete. So what we're saying is that if you have a polynomial 3x cubed plus 2x squared plus x to the 1 plus 1, say. Okay, that we're saying that this is basically going to be like 3x cubed when the absolute value of x is large. Okay, so yeah, this is actually really handy, right? If you don't understand something in the abstract, put some numbers in and make it concrete. Okay, that's a useful thing to do. Okay, why? Well, let's rewrite this thing. 3x cubed plus 2x squared plus x to the 1 plus 1 is the same thing as 3x cubed times And now I'm going to factor out this 3x cubed out of everything here, right? It'd be 1 plus 2/3 x to the minus 1, right? Because when I multiply that times this, I'm going to get 2, the 3's will cancel, and I'll get x squared, right? That'll give me my 2x squared, right? And then I need 1/3 x to the minus 2, and then I need, again, 1/3 x to the minus 3. Okay, so that's all I'm doing over here. I'm just writing it in the general form so that this can encompass any polynomial, right? In this case over here, right? This is my, in this case here, this is my a sub 3. This is my n, right? This is my a2. This is my n minus 1, right? This is my a1. This is, you know, this is 1, and then this is a0 and 0. Yeah, Lisa.
Why would it be a and 0? Like, why are you using n and then 1 and then 0? Like, could you substitute like for the same problem on the left?
Yeah.
Why would you use n and then 1 and then 0? Would it,
Well, I'm going down from you know n minus 1 dot 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 down to 1 down to 0. Right, just like over there, I went 3 2 1 3 2 1 0. Right, you know, depending on what n is. If n is 10, it's going to be 10 9 8 7 6 5 4 3 2 1 0. But it's always going to end with 1 0. So I read this as 1 0. Yeah. Okay. Okay. Yeah. Yeah. It takes some getting used to. It takes some getting used to, like this abstract, you know, writing things in the abstract. And like I said, a good way to get more comfortable with it is to make it concrete. Put some numbers in and say, okay, what does this mean for an actual polynomial, right? This means that if you took an actual polynomial and factored out, you know, the top term, you know, and distribute out the top term, you'd be left with this weird thing, right? So the question was, remember, why is this thing basically like the top term if the size of x is large? If the size of x is large. Well, let's think, okay, if x gets really huge, what's going to happen to this x to the minus 1? So as x in size gets really huge, heads off towards infinity, what's going to happen to x to the minus 1? That's 1 over x, right? As x gets huge, that's going to go to 0. Right? What's going to happen to x to the minus 2? That's 1 over x squared. Right? It'll also get really small. It'll get even small even faster, right? It's going to go to 0 even faster than this guy. And this guy will go to 0 even faster than that guy. Right? So all these terms are going to shrink, right? All these terms, so as these go, this, right? This whole thing over here turns into 1. Right? Because this term is going to go to 0, this term is going to 0. All these terms over here are going to go to 0. The only thing that doesn't get affected is this 1 here. Right? And so you end up with 3x cubed. Okay. So that's literally what it's going to be looking like, you know, as you head off towards infinity. Right? And you say the same thing over here. So as absolute value of x goes to infinity, the term in brackets, the bracketed term, goes to 1. So polynomial becomes basically like the top term, a sub n next to the n. Right. This kind of thing you're going to see a lot next semester if you take Calc 1. This is called taking the limit as x goes to infinity. The limit as x goes to infinity. So limit is the idea of calculus that makes calculus different from everything that came before. And this is one instance of it. Right. calculus, like I said before, is taking, studying things that you don't know by taking things that you do know and then combining it with this idea of limit. Right? Taking the limit as you get infinitely close in some way. Okay. Anyway, so just to give you some sense of how in mathematics we would say that this thing it becomes basically this top term. Okay. So the last thing we're going to do in this section about polynomials is to get some way of graphing them. Some way of graphing them. Okay. So we sort of know this before. So we have some knowledge of this. From before. Right, so here's an example. If I have a polynomial and it's x times x minus 3 times x plus 3, say, it factors like that, then if somebody said, what does that polynomial look like? You would be able to give some information about it, right? Like, where does it cross the x-axis? Just look at it. Where does it cross the x-axis? 3 and negative 3, 3, negative 3, and 0, right? So you got these 3 points, 3, negative 3, and 0, so you know it crosses at those points, right? And you could plug in intermediate points and tell where it's positive and negative, and that would tell you that it's negative, positive, negative, positive. Okay. So I'm not going to make you do it. So you would know that it goes something like this. Which you actually know already because it's a degree 3 polynomial, and so you know it's going to look like a cubic. You know it's going to look like a cubic, and so you didn't even need to plug in these things, because you know that it's a cubic and it's got to start down here and it's got to end up there, right? And it's not gonna. Anyway, so you actually don't. At this point, you actually don't need to plug in things. You have some better sense of it. Okay. Here's another one. P of x is x squared times x minus 4 times x plus 2. This one's a little bit more complicated, but in any case, where does it cross the 0? Where does it cross the line y equals 0? Where are the zeros? Go ahead. 4, and negative 2. And 0, right? And this is a degree 4 polynomial, so we know it's going to come down and then go back up eventually, right? So at least we know that it's going to do something like this, right? Right. So if you checked the signs, you see that it becomes negative. It's negative here and it's negative here. Okay, so you know that it goes like this. And if you thought about it, knowing what you know about, that it's a degree 4 polynomial, you'd actually be able to figure out that that's what has to happen. Okay, so this is what we know already, right? This you were able to do already, just from previous knowledge. Okay. But we can actually do something a little bit better than that. Using a fact that, so again, I'm going to put up this fact, hopefully believable. Here it is. If the polynomial has a 0 of degree n at some point a, so let's translate that. So like example, the second polynomial, this one has a 0 of degree 2 at 0, of degree 1 at 4, and of degree 1 at -2. Okay, so I don't think I've introduced this terminology before, but based on the power here, you call that a degree blah polynomial, degree blah 0. See, this guy has a 0 there, right? It's a degree 1 0. Okay, this is also a degree 1 0. This is a degree. This gives us degree 2 0. Okay, if it were like this, then this at 4 we would have a degree 3 0. Okay, right? If it were like this, then at -2 we would have a degree 4 0. Okay, you guys get that? So so P. I'm just gonna leave it that. I don't want to write it out. Okay. So if your polynomial has a degree n0 at some point a, then near a, p of x looks like a times x minus a to the n, where a is px over x minus a to the n evaluated at a. Okay, I know that looks a little bit like that maybe looks incomprehensible, but it will become clear when I show you how to do it. Okay, let me show you what that really means. What does that mean? What does that mean? So let's go to our first guy here, right? So p of x is x minus 3, x plus 3, right? It's got 3 zeros, right? It's got 3 zeros. Zeros at 0, 3, and -3, and what this tells us is that near 0, p of x looks like some number times x. Okay. Where the way you get this number is you just plug in 0 to these other guys. Okay. So this. Effectively, what this says is that if you're near 0, then your polynomial basically looks like x. You take the term involving this guy, and then you just plug in 0 to the other guys, right? You're gonna have a -3, and you're gonna have a +3, so you get -9. Okay, so you get -9x. Okay. Right? So near 0, it's going to look like -9x. Okay. Right? Near 3, well, you've got this guy, x minus 3, x plus 3. So we're looking where around this 0 here, right? And what we say is that, okay, this is basically going to be x minus 3 times some constant that you get by plugging in 3 for these other guys. So you'd say you've got a 3 here, and you've got a 6 here, so you got 18. Okay, so you know that this thing is going to look like 18 times x minus 3. Okay, near negative 3, I'll let you do it. What is it going to look like near negative 3? Well, near negative 3, this is the term that gives us that that 0, right? So we're going to have that term, and we're going to be multiplied by some constant. We get the constant by plugging in the negative 3 to here, right? So this is going to be negative 3, this is going to be negative 6, and we get 18 again. Okay, so what does that tell us about our function? It gives us a better picture. Here was negative 3, 3, 0, right? We know that it crosses there, but now we know something a little bit better. That near negative 3, it looks like 18 times the line y equals x moved over 3 units, right? Right. It looks like this line, it looks like the line y equals x multiplied by 18 and slid over 3 units, right? So it's going to look like something of slope 18, a line of slope 18, right? Similarly, near 3, it also looks like a line of slope 18, okay? And at 0, it looks like a line of slope 9, so that's the slope is half as steep, okay? So that tells us that the graph actually looks something more like this. Right? It gives us a better understanding of the behavior near the zeros. Okay, so you can actually tell really pretty precisely, how the thing behaves near zeros. Right? So this is about like more accurate understanding near zeros. Let me quickly run through the second example. So second example, p of x is x squared, x minus 4, x plus 2, right? So we have 0, we have 4, and we've got minus 2. Those are the zeros, right? So when x is 0, we know that it's going to be, p of x is going to be basically x squared times negative 4. We just plug in the 0 here. We get negative 4 times 2. We get negative 8. At x equals 4, we're going to get, it looks like p of x is going to look like x minus 4 times, we plug in a 4 here, so you get 16. 16 times 6, that's 96. Right? And at negative 2, we get that p of x looks like x plus 2, and we get negative 2 minus 4, that's negative 6, times 4, so we get negative 24. What does that tell us? That at 4, we've got this super steep slope, a slope of 96, right? At negative 2, we've got also a fairly steep, but a fourth is steep going downwards, negative 24 slope. And then at 0, we've got negative 8 times x squared, right? So we have the x squared function. We stretch it up and we flip it over, right? So we stretch it and we flip it over like that, right? And so our function is going to look something like that. And you see that this is way more detail than what we had before. So this is kind of a cool thing to know the behavior near zeros for polynomials. Okay. Next time we'll do rational functions, and we'll do almost exactly the same game. I do have exams if people want them. Do you guys want your exams? Okay, let me give it to you. I haven't added on the points from the SQAs, so it may go up slightly.